Okay. Hello, everyone. It's 10:10. I guess people are still coming in, uh, but I'll sort of start with some introductory remarks, uh, as usual. There's a homework due this Friday, and it seems that everything is pushed back. So I'll change the due date for the next homework for next week, um, and I will. By the end of the week, we should have a date for the first midterm, and I'll let you know about that. And today there are the discussion sessions with our class TA. So one at 11:30 and the other one at 5, just a reminder. So I encourage everyone to attend those. Those are quite useful, I think. And you can get other questions and discussions that you may have addressed during those times. Okay, so I'm going to continue our discussion now. So I'll open up the floor for any questions, comments, or points for discussion if people would like to do so. And if so, just chime in and then we can discuss. Okay, if not, then I'm going to continue. We talked a lot about reversible processes, and it's an idealization. And last class we concluded that the reversible process is an optimal process when it comes to work, in the context of work. So the reversible work, or the differential of the reversible work for a process, is always going to be less than the work that's involved in an irreversible process. And this was our conclusion. Okay, and that means that if the system does work on the surroundings, you'll get the most out of a system when the work is done reversibly, or when the system undergoes a process reversibly. And if the environment surroundings have to do work on a system, the least amount of work that has to be done on the system to effect a change is when the process is done reversibly, when the system is changed reversibly from one state to another, and that interaction, that is the work interaction, is reversible. Okay, so these are and so it doesn't matter whether the system does work or whether the environment does work. These inequalities are general and whole always. Okay, so let's just, before I move on to a consequence of this, I just want to make sure we can compute reversible work for an ideal gas equation of state. So as an example, and I think you've already seen this, I'm just going to do it very, very quickly. So if you have your ideal gas equation of state, which is PV is equal to nRT, we can compute the reversible work, which is equal to minus pressure, which is a function of temperature, volume, and N dV. And the differential of this reversible work, if we solve for pressure using the ideal gas equation of state, this becomes minus nRT 1 over V times dV. So all of this, if you will, and I'm going to make that red just so you know, this guy in red is our integrand. Okay? And then the dV is signifying that this is a differential form. Okay, so what's in the red parentheses is the integrand. Okay. Now, for an isothermal process, and reversible, of course, because now just by writing this equation, we said, or we've indicated that the process is reversible, because we can even write it this way: P external is equal to pressure, temperature, volume, and N. Okay, what this is saying is that the external pressure is equal to the system's equilibrium pressure as given by some equation of state. Okay, so that's what reversibility means. We saw that, remember, when we go really, really slow in terms of a compression, the external pressure is always differentially different than the system equilibrium pressure. So for an isothermal reversible process, going back to our calculation of work, we know that in our integrand, which is given in the red parentheses, the temperature is a constant because it's isothermal. Okay? So this dW reversible is equal to minus nRT times, we can write this now dV over V, okay, which is equal to minus nRT 1 over V dV, if you will. It's all the same. There is no, there are two different ways. We can further write this dV over V as minus nRT d natural log of V. Remember, dV over V is just d log V. And you can see that, just to refresh your memory, if your function is natural log of V, which is the natural log of volume, okay, the derivative with respect to V, derivative of natural log V dV is just equal to 1 over V. We call natural log x, the derivative of natural log of x, d natural log of x dx is equal to 1 over x, right? So this is the same thing. We just replace x with V, and we can write d natural log V is equal to 1 over V times dV if we bring over the dV, the differential in volume. And so we see that d log V is 1 over V dV, or dV over V. And this is what we have here. Okay, and so that's why we can write this expression now as d log V. Now it's just a matter of integrating to get the work that's involved in this process. That would be involving a change of volume, because we see here in this differential that volume is the thing that is changing. That's the parameter that is changing. So now we don't have a differential, we just have total work. There's no delta work, there's just W is equal to the integral of dW reversible from state 1 to state 2. And that's going to be the integral from V1 to V2 of minus nRT d natural log of V. Okay. And this is just going to equal minus nRT, because t is a constant and everything else is a constant. Integral of, from V1 to V2 of d natural log V. But this is a very interesting and very simple integral, because you can think about this part, right, as an analogy, just as the integral from x1, x2 of dx, right? That's all this is. And we know, so I'll write here analogy just to help you understand what that is. So when you take the integral from x1 to x2 of dx, that's just going to be x evaluated at x2 minus x evaluated at x1, right? This is just equal to x2 minus x1. Okay, that integral. So the integral of d log V is just going to be log of V evaluated at V2 minus log of V evaluated at V1. And what that gives us then, let me just move this a little bit. W reversible is equal to minus nRT times natural log V2 minus natural log V1. Okay, so it's not natural log of the quantity V2 minus V1, it's natural log of V2 minus natural log of V1. Okay, and then we can go on to further simplify this, minus nRT natural log V2 over V1. And so this is what we get as the reversible work for an isothermal process which involves a change in volume with a gas that's represented or modeled using the ideal gas equation of state. And so this applies for an expansion or a compression. And so I think you'll see this so much in this course that you'll memorize it. It just comes up everywhere. Okay. And so for an expansion, or when, let's say, system does work. Oops, I'm writing it twice. System does work on surroundings. We know beforehand that W reversible should be less than 0. It should be negative because that was our sign convention. So let's see what happens here. If the system does work on the surroundings, V2 will be greater than V1. It's like an expansion. So here we can say that IE, we have an expansion. IE means, for example, we have an expansion of our ideal gas. Okay, if V2 is greater than V1. In that case, natural log of V2 over V1 will be greater than 0. Right? Because natural log of something that's greater than 1 is going to be greater than 0. V2 will be greater than V1. So the argument is going to be greater than 1. And since everything else in the equation for reversible work is positive, except for that minus sign at the beginning of that expression, work reversible indeed will be negative for this case where the system does work on the surroundings. For example, an expansion of an ideal gas. Okay. And now, if the surroundings do work on the system, we know a priori, we already know that W reversible will have to be greater than 0. And so again, in this case, if we say there's a compression of the gas due to some due to some mechanism in the surroundings, V2 will be less than V1 because we're compressing, so the final state will have a smaller volume than the initial volume. Natural log of V2 over V1 will be less than 0 because now V2 over V1 is less than 1. Okay, and when you have any fraction as the argument of a log, you get a negative log for that combination. So W reversible will be positive, greater than 0, because we have to multiply this negative term by the negative sign that's in front of our expression for the work. Okay, so natural log V2 over V1 is negative. We multiply it by the negative sign that's all the way in the front there, and we get a positive work, and everything works out. Okay, so in this case, we see that that's our reversible work for an isothermal process involving an ideal gas. Okay, and so I reiterate that this is for an isothermal process. Okay, that's why it's called isothermal and reversible. And this is for a gas that's modeled by an ideal gas equation of state, which is this. Okay, any questions, comments? Okay, and this would be the maximum work out that the system would do on the surroundings, or the minimum work that the surroundings would have to do on the system. So if we were going either compression or expansion between V2 and V1, the system would give us the most work during the expansion. And if we were to do the compression, we would have to do the least amount of work. In both cases, letting the process happen reversibly. Okay? And that's what's special about the reversible process. Okay, so that's the ideal gas equation of state. I'm going to introduce another equation of state, which is a step above the ideal gas equation of state. And I'm going to ask you all to figure out the reversible work for this equation of state. Okay, because I think it's a good exercise, and it's actually not that difficult. So this is another equation of state that we'll use in this course often. It's called the van der Waals equation of state, after a Dutch scientist. Okay, so this is the van der Waals equation of state. And now what it does, it takes into account two things. Okay, so it improves and I'll put that in quotes because it's still not the most perfect equation of state. There are other ones that are much more accurate, but they're much more complicated. So this equation of state improves upon the ideal gas equation of state. Okay, and the way it does so is by one, it accounts for finite volume or a finite size of real particles. Okay, and a particle may be a molecule or an atom. Okay, so particles could be, i.e., atoms, molecules. Okay, so whether you've been told this or not, one of the implicit assumptions of the ideal gas equation of state is that the particles are point particles. Okay, they effectively have no volume or no size. This is an implicit assumption. If you're applying this to real gases, it applies to real gases in dilute limits. So under low pressures or where the density is very, 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 very low. And in those limiting conditions, you can treat these atoms, these particles, as point particles without any finite volume or size. Because if you're a particle, again, be a molecule, it always helps to be a molecule when you're thinking about chemical things. If it's a very low density gas, if you are part of a low density gas, you're not really going to see another particle. The other particle is going to be so far away that to you it seems like a point. Okay, so you can imagine, in your own real physical world, that if something is far, far away, it almost looks like a point. So this is the physical intuition or approximation that goes into the ideal gas equation of state. So effectively, particles are point particles. They have no real volume, or finite volume, sorry, or size. And so the van der Waals equation of state accounts for this by introducing a volume for a particle. And I'll show you how in a moment when I show you the equation. The second way that this equation of state improves upon the ideal gas is by accounting for particle-particle interactions. Again, in the ideal gas case, I know everyone has been introduced to the notion that ideal gas particles don't interact, right? Well, in this equation of state, they do. And that's taken into account in a direct way. Okay, so these two actually, in the ideal gas case, right, because point particles, or if a particle is so far away, obviously you're not going to interact with it. So it's a self-consistent set of assumptions for the ideal gas. It's rather self-consistent. So the van der Waals equation of state, I'll write it in terms of pressure, okay, and we'll write that in terms of temperature, volume, and the number of moles. So this is the equilibrium pressure. Remember, equations of state give you equilibrium system properties as they relate to one another. And that's going to be nRT divided by V minus N times B minus AN squared over V squared. Okay, so this is the van der Waals equation of state. Okay, here I've isolated the pressure because often, what we need for work is P as a function of temperature, volume, N, and in this form it's very nice that it's already there in that form. So the way the van der Waals equation of state takes into account the finite size of particles is through this parameter. There are parameters here. There's two. One is B, okay, and that's given right here. That's B. And the other one is A, and that's given here. Okay, so you have B and A. So B accounts for the size or the finite volume of a particle. And you can see that because this term where you initially had just the V, remember in the ideal gas equation of state, if you disregard in the A N squared over V squared term for the moment, and if you disregard the NB term, you retrieve or you recover the ideal gas equation of state. But here, what we're doing to the volume is we're effectively reducing the volume that's available to a particle by this amount that is taken up by other particles. So B represents the volume, is a volume parameter per particle. And so if you multiply it by the number of moles, N, essentially you have the volume that's taken up by the particles that you have in the system. So V is the system of the volume of the system. So it's the let's say you have a container, that would be the total volume of the container. And then if you subtract out the number of moles times this V parameter, which effectively gives you the volume per particle, and you can convert particles to moles by Avogadro's number. It's a very simple conversion. You see here that the van der Waals equation of state is effectively accounting for the finite size that particles take up in the volume, in this container volume. Okay, so B is a volume parameter. And these parameters are something that is fit. You have to have experimental data. So now you would take real gases and you would effectively compute or measure pressure of the gas at different volumes or at different temperatures, relate them through this model, and then fit through nonlinear regression these parameters. Okay, so B is the volume parameter. Don't worry about the regression or the fitting. Just for the moment, all we're concerned about is what the physical meaning is of B, and that is that it's a volume. And you can see that it's a volume because it's subtracting from the system volume with the container volume B. A, the parameter A, accounts for the point B, interactions between particles. And it's a pair interaction, so it's between pairs of particles, interactions between particles. Okay, and you can see how that comes about because if you have interactions between particles, okay, in a container, we know that pressure represents an average force that arises from the collisions of particles on that wall, on the walls of the container. Okay, so if you think about classically, we're not looking at quantum wave functions for the moment. That'll be next semester. But if you're just thinking about a container where you have gas, and you think about the gas particles as little spheres, okay, since they have kinetic energy and hence a temperature, they're hitting the walls. And when you hit something, you're applying an instantaneous force. And that force then over the surface area of your container is a pressure. Now, in this model, we see that that second term is subtracting from the pressure. So it's subtracting from the first term. And why that is because if you have particles that are interacting now, as opposed to the case of an ideal gas where particles don't interact, if you have particles that are interacting, when a particle hits the wall, it's not as forceful as it would be, or as it would had it not be, if it were not being attracted by other particles that are not near the wall or further away from the wall. So if this is your wall, right? If you have no interactions between particles, particles can hit the wall, okay? But now, if you have interactions between the particles, a particle moving towards the wall is going to be attracted away from that wall to a certain extent by other particles. And hence, the force that it exerts on the wall will be less, because one reason being that it's moving slower, potentially, okay? And so that's how this van der Waals equation of state takes into account interactions. So this is a step above the ideal gas equation of state for these two parameters. So what, and we will be using this a lot in this course, so it's good to know a little bit about it. Okay, and so it's an attempt to model non-ideal systems. So we can call this an equation of state for non-ideal systems, non-ideal gas, okay? Or a real gas, if you want to call it that. But of course, I put real in quotes because, again, this is just an approximation. Okay. So I encourage you, I'm not going to do it here, but I encourage you all, and I think this might even be done in your text, but if not, compute the reversible work that you would have, which is minus dTVN dV, using the van der Waals, and I'll call that VDW, equation of state. Okay, so Take a few moments when you have, whenever you have a few moments today, whenever, and just do that. It should be very quick. And the solutions of that are all over the place, so you can check whether you've done it right or not. But I want you to take a crack at it for yourself. Okay, any questions on that? Okay, awesome, great. So let's move on. Next points that I want to address. All right, so that was a whole bunch of stuff on work. All right, now we're going to go back to the first law and sort of address a few things. Okay. So that's reversible work and a lot of the consequences of that. So let's go back to the first law and focus on a few things called constraints. So let me remind you of the first law, okay, in differential form. Okay, so the differential form of the first law, du is equal to dq plus dw, okay? And we see here that it's a way to convert heat into work and work into heat. Okay, that's what really this is saying. And if we were to do the integrated form, so this is the differential form, which is what we will be using. But the integrated form, if you integrate this over a cycle, we know that the integral of du over a cycle is equal to 0. Because remember, u is a state function, and that's equal to the integral over a cycle of dq plus dw. Okay, so this is the integral form of the first law. Okay, but we'll use the differential form because that's very useful for us. And I remind you, u is a state function. Okay. So therefore, it only depends on initial and final states. It's path independent. It's not path dependent. Okay. It's not path dependent. Okay. So it's like temperature, volume, pressure. Okay, just like those guys. It's not dependent on path. All right, so if we now know our expressions for heat and work, we can actually get some insight into what we can do with the internal energy. So let's take a look at this. du, we know that dq is equal to c path dt. And we know dw is equal to minus p external dv. So this is a very general form now. What I've done here is substitute what we know for dq and dw. Okay? So we can write du, our differential form for the internal energy u, or the energy u, as the specific heat, which is path dependent. Remember, there is a constant pressure specific heat and a constant volume specific heat. So that's why this is C path. This is path. And then we have minus P external dV for the work. And that we've seen so much now that that's pretty, it should be pretty straightforward. Okay. What this seems to suggest, based on these differentials, and what we know of differential calculus, that if the differential or a change in u is associated with the change in dt and dv, it must mean or must imply that u can be written as a function of temperature and volume. And we'll leave out n for the moment, okay? But u is extensive the way we've defined it here, okay? So u is extensive the way we've defined it, but I'm going to leave out n. So what our first law is telling us is that as a first pass, we can write u as a function of temperature and volume, okay? Because the total differential, that's what this is, the total differential. The total differential of u depends on a term that is a rate of change in T, dt, and there's a term that's representing the change in volume, which is dV. Okay. So is that clear to everyone from this representation of the first law? Okay, good. We can actually abstract this or generalize this, and I will before I go on to the issue of constraints. I can actually write du in a much more general way, which we will use to gain some insights into some system properties. So du, starting with this guy, okay, we can actually see that now we can write that du is a function of u is a function of temperature and volume. Now we're going to use our concept of partial derivatives. Okay, so u is a function of two variables. U is a function of temperature and volume. Okay, we won't let n change, so we're not going to worry about that for the moment. Okay. So u is a function of temperature and volume. So if we're looking at the total differential of u, okay, u can only depend on temperature and volume, the way we've written it here. Okay, the way we've written it here. So u will change by a certain amount if T changes by a certain amount, or V changes by a certain amount, or both. Okay? So if T and V change, U will change, and that change in U is the total differential, which is given by du here. Okay? And we call it total, even though it's a differential, but you see it's the total differential. It's not the total delta, it's just the total differential. And it's called total because it's going to have to include the contributions that arise from changes in T and the changes in V. And you'll see that in a moment. If it's total, then there must be some summation. Okay, one might think that, oh, okay, this is a total differential. If it's a total differential, it's going to have to be a summation of things to get a total. Okay? So, in fact, that's what it is. And in this case, you will have a summation of two things that total to the total differential. Okay, and those two things are as follows. One is going to be the partial derivative of u, which is a function of temperature and volume. So when I write u, left parentheses, t comma v, right parentheses, what I'm indicating is that u is a function of temperature and volume. So this first guy is going to be the partial of u with respect to t. Okay, that's what that term is. But we're going to qualify this by saying that, all right, we're going to hold volume constant when we take this differential or this derivative, okay? And so this is sort of getting us used to the idea of partial differentials. So what this is saying again is that we're going to take the partial differential or the partial derivative of u with respect to temperature while holding volume constant. Okay, so if we were to do an experiment, the volume would be constant. We would vary the temperature. And then if we could measure u, we would measure u at those various temperatures. Okay. What this sort of signifies is a rate, right? You can see that this is the rate of change of u with respect to t. For a given change in t, you get a change in u. So if I were to multiply a rate by the thing that the rate is per, in this case temperature, I would do this. Okay. And so if I multiply the partial of u with respect to t at constant v times dt, what I get is the change in u for that small change in t. Okay, that's the contribution I get for that small change in t. And you can see that because the temperatures cancel, right? You have a t on the bottom, and then you're multiplying it by a t, right? So that gives you the change of u for that change in t. Okay, to get the total, we still need to account for the changes in volume. So now we add our summation. So we add a plus, and this time we have the partial of u with respect to the other variable that it depends on, v, which is the volume. But this time, what do we have to hold constant? Well, this time we have to hold temperature constant. And since that last term is a rate of change, it's the rate of change of u with respect to any change in volume, we multiply this by dv. So in this form, we see that the total change, or the total differential of U, which is given by this guy, that's in mathematical symbols, the total differential of U is written that way, is equal to the sum of the change in U arising from temperature changes and the change in U arising from volume changes. And we only consider temperature and volume changes because U, we have selected, or we have chosen to be dependent on temperature and volume, as signified by U parentheses TV. Okay? Now, is that clear? Does everyone see how we get a differential change in U on the left arising from a rate times this dt plus a rate times dv? Is that clear?
Yes.
Okay. Okay. And if it helps you, you can even use units or dimensional analysis. So on the left-hand side of the equal sign, we have units of U in energy. Those are the only units. And if we look at the right-hand side, for the first term, we have units of energy over temperature. We multiply it by temperature, then we get units of energy for the first term. And then for the second term, we have energy per volume. We multiply that by volume, so we are left with energy. So the two terms on the right-hand side, they give you contributions with units of energy, and that's what you should get on the left-hand side. And so everything is consistent here, okay? And so the first law, when we wrote, derived it, or well, when Joule came up with it, with his heat and work interactions, he essentially gave us some insight as to what possibly could be the first things to try as variables on which U depends, and that's temperature and volume. And so this is what we get here as a general way of thinking about U and its total differential. Now, these partial derivatives have special meaning, okay, other than what we've seen here in terms of the first law. And so we're going to address that soon using the Joule experiment, the Joule free expansion. That's why I want everyone to understand this guy. Okay, so if there's any questions at the moment, please let me know, and we can stop here and discuss this. And if not, then I'll just go on. Okay, great. So before I do that, I just want to go through some constraints. We'll get to the Joule expansion in a moment. Constraints are going to be very important in this course, okay? Because it's because of constraints that things such as the Gibbs free energy, the enthalpy, Helmholtz free energy, if you've heard of that, arise. And they arise because of constraints. Okay? And so it's good to sort of understand what they are, and in the context of what we've done so far, we can sort of introduce a few constraints and see what the consequences are. Okay? All right. So the first one, you may not think of this as a constraint, but we can always think about it that way, is that a process is reversible. Okay? And in which case then, du, and now we're going to look at constraints and how they relate to the first law. Okay, that's what we're doing now, and how they relate to the first law. So everything will be a first law related kind of a discussion. So we know that for a reversible process, we have dq reversible plus dw reversible. Okay. And so for a reversible process, this is just going to equal dq reversible minus pressure Tvn dV. Okay. So as you may have seen already in some of your problems, or in future problems, if you're given a reversible process in a first law type of problem, you know that you can already use that constraint that the process is reversible, to write down this expression. Okay, you already know that. So constraints allow us to sort of now become more specific in terms of problem solutions. All right. If you have an isolated system, okay, well, this is actually the easiest one, right? This is it's like the universe. So for an isolated system, dq is going to be 0. dw is going to be 0 if you have an isolated system. There's no interactions. And so in this case, then du is going to be 0. Okay, that's another constraint that may be imposed upon or used in a problem. Another thing, I haven't discussed this, but now we can introduce this idea if you haven't already seen it in your readings, is if something is adiabatic. Okay, so you may have an adiabatic process. Right, did I spell it right? Yeah, adiabatic. And so for an adiabatic process, okay, for an adiabatic process, dq is equal to 0. There is no heat interaction. Across a boundary. Across a boundary between system and surroundings. Okay, no heat interaction across the boundary. And that's very important. So dq is 0. So du then is going to equal dw. Okay, everyone follow so far?
Yep.
Okay. So what, does this strike anyone as a little strange? There's a few things I want to discuss here in terms of the types of functions that we have on either side of the equal sign. If we look at this case, because of course dq is 0. dq is 0 for an adiabatic process. So we have du is equal to dw. From what we've discussed about the nature of u and the nature of w, does this kind of seem strange?
Yeah,
Okay, why?
because one is path dependent and one is path independent.
Exactly, that's exactly right. So you see here, u is the path independent function and w is this path dependent function. And yet when you have an adiabatic process, the two are the same. So if an adiabatic process between two equilibrium states, okay, if you have an equilibrium, if you have an adiabatic process occurring between two equilibrium states, we have a situation where something is going to have to be modified here in this equation. Okay, so which one of these two, in the most general sense, if you're going between two equilibrium states, is very well defined and can never vary? If you have two equilibrium states, 1 and 2, is it u or w that can never ever change depending on the process or depending on the path? Which one is always going to be the same?
Be you.
Exactly, u. U will always have to be the same number if you go between equilibrium state 1 and 2, regardless of the path. Okay, so if you go from equilibrium state 1, here's, oh, that's a bad choice. Why not? Doesn't matter. Here's equilibrium state 2, and if you go along some path, okay, or if you go along some other path, right, delta u is always going to be the same. Okay, du will always have to be the same because u is a state function. It doesn't depend on the path. So that means there's a unique value on the left-hand side. Okay, there's a unique value on the left-hand side for u. If we were to integrate this, we would get delta u is equal to w. Okay, just by integrating. All right, so what does that mean? What do we have to, so how do we get a unique value for w then, for a process? What would have to be a characteristic of the process?
pressure?
Oh, what about the pressure?
Would it have to change from state from it would have to change from volume to volume?
Okay. And how would we describe that pressure?
Maybe P external or delta P?
Would it be P external?
It'd just be P.
It would be P, right? And so if we use P, what are we implying about the process? We call the isothermal process for an ideal gas.
Is it isobaric?
Well, this is isothermal, but what is the nature of the process in a more general sense? Okay, let me, yeah, this is difficult to ask the question and even to answer it. Reversible. Remember, for the reversible process, there's only one work associated. It's going along this path. Remember, if you go through a process that's anything else other than the reversible, you're going to get different values of the work. Because in last class, we saw that we could effect this change through two stages. Remember, first we dropped the pressure to this point, and then we went this way, and then we dropped it to this point, and then we went this way. So overall, the work that we obtained was this, if we did it irreversibly, whereas the area under that blue curve would be the reversible work, right? And there's only one value of the reversible work. That's that area under the curve, okay? However, if you do that irreversible process in two stages with those great lumps of sand that we did last time, you get the work that's under the two red rectangles. You see they're different compared to the the reversible case. You could actually do this. And I'm going to do the easy one because then the pictures get too cluttered. So here's our reversible, same as the top graph. But now what I'm going to do is drop that pressure really, really violently to the final one. And so what happens then is I get this as the work done. So you see here that for an irreversible process, I have many choices to go from state 1 to state 2 irreversibly. And for each one of those, I'm going to get a different work. In the top graph, I did two stages of irreversible work. And those are irreversible because they don't follow that blue curve. Okay, that blue curve is the reversible curve. And in the bottom one, I only did one stage of irreversible work. And the work that I get out is through that magenta or purple box. So you see the works are different. And so for this constraint, when we have an adiabatic process, if we want to equate a state function, which is path independent, to something that ostensibly is path dependent, we need to have a unique value of that path dependent function. And the only way to achieve that is to compute it or to evaluate it through some process that is reversible. In which case, then we have one and only one unique value of that work. Okay? There is only one and only one unique value for reversible work between two endpoints, two equilibrium states, 1 and 2. And this illustrates that point. Okay, so the blue curve is reversible. And if you look at the two cases where you have two stages of irreversible, okay, here in the top, you have two stages of irreversible work. And in the bottom, you have one stage of irreversible work. And it's irreversible, why? Because we violently or instantaneously change the pressure on the system in both cases. In the second case, we go to the final pressure instantaneously. In the top case, we go to the final pressure in two stages. So the jumps are a little less, but nonetheless, they take the system out of equilibrium, and because the system is no longer in equilibrium, those two processes are irreversible. Okay? So ponder that little subtlety, but that you were able to pick that out is very good. I'm very pleased. Okay, as usual, I've talked too much. There's a few other constraints that we will talk about, and then next class we will do the Joule-free expansion experiment, and then I will introduce enthalpy, which is the next thing that next state function that we will address. Okay, any questions, comments, requests for clarification? Okay. Great. So again, I urge everyone, encourage people to go to the discussion sessions, and I wish you a great rest of the week. Thanks for your participation once again. Okay, so I'm going to end the meeting then, okay? All right.
Thank you.
All right.
Have a good day.
Thank you, you too.
Thank you.
Yep, thank you.